Hi everyone, welcome to BazelCon 2021. I'm Yun from the Bazel team.
I'm Xudong, also from the Bazel team. We both work on the Bzlmod project.
Managing external dependencies remains one of the biggest user pain points for Bazel. In last year's BazelCon BOF session, we announced that we are going to develop Bzlmod, the new external dependency system for Bazel. In the past year, we have been continuously working on this project and iterating the design details along the way. Finally, we can present the latest project status here. In this talk, we'll explain Bzlmod in the following sections. I'll start with Bazel modules and Bazel central registry. Xudong will then talk about module extensions and our progress and future plans. Let's get started. So in the new world, every Bazel project is a Bazel module, which defines dependencies in the module.bazel file at its source root. As you can see, you can use the module directive to describe properties of your own project, and use the Bazel dep directive to declare dependency on other Bazel modules at a specific version. Each Bazel dep is fetched from a Bazel registry and will generate a corresponding external repository. By default, the repo name is the same as the module name, but you can also specify it using the repo name attribute. Unlike the workspace file, you don't have to declare all of your transitive dependencies, but only the ones you depend on directly. Bzlmod will discover the dependency graph by reading the module.bazel files recursively. However, this also means we have to do dependency resolution when there are conflicts. So how do we do that? We use the minimal version selection algorithm to resolve the dependency graph. It's a very simple algorithm introduced in Go's dependency management system. In short, it assumes newer module versions are backwards compatible. Therefore, it can always select the maximum module version that appears in the dependency graph. For example, in this graph, A is the main module, which depends on B1.2 and C1.2. In the resolved dependency graph, D1.4 is selected because it's newer than D1.3, and E1.2 is selected because no newer version is required even though E1.3 exists. MVS works well in Go because all Go modules follow semantic versioning. However, we can't enforce that on all Bazel projects. So when your project has to ship incompatible changes, you can declare the compatibility level in the module directive. For example, here, say 1.2 has compatibility level 1, and for say 2.0 it's increased to 2. It basically follows the increase of the major version number if your project already uses semantic versioning. During dependency resolution, a module version with a different compatibility level is considered to be a different module. By default, we don't allow multiple versions of the same module to coexist in the resolved dependency graph because Bzlmod has no idea if it will cause any issues during build time. But the end user can use multiple version override directive to explicitly allow that if they think that's okay. While multiple version override is a bit magic, we do support other normal overrides to help you pinpoint a module to a certain version. As you can see, you can specify a different registry or version, a local path, a commit from Git repo, or an archive URL to override a specific module. Using overrides also affects your dependency graph. For example, if C is overridden to a local version which depends on E1.3, your resolved dependency graph will change accordingly. While those overrides are useful during development for testing and debugging purposes, to avoid unnecessary complexity, they are only effective in the module.bazel file of the top-level project. Therefore, they should be removed before you publish your project in a Bazel registry. Finally, we are enforcing strict depths on external dependencies, which means a Bazel module can only see the dependencies it directly declares. For example, in this case, even though module D is available in the resolved dependency graph, it's not possible for module A to use any targets from D unless it explicitly declares D as a direct dependency. This helps make sure your build still works correctly after updating your dependencies. So next, Bazel Central Registry. As I mentioned, Bzlmod fetches Bazel depth from Bazel registries. A Bazel registry is an index of Bazel modules. To create a more unified ecosystem, we initiated the Bazel Central Registry. It is a recommended place to publish your Bazel open source projects. We manage the Bazel Central Registry on a GitHub repository and mirror the content of the main branch to a static website, registry.bazel.build. Because it's a GitHub repo, anyone can contribute to it through a pull request. So what do we host in the BCR exactly? For modules checked in the BCR, we don't store their full sources. Instead, we store a source.json file for each module version to indicate where to download its source code archive. You can also store patch files in the registry in case you cannot upstream the change. For example, adding a build file for some non-Bazel projects. And for both the source archive and the patch files, their contents are verified by an integrity value. Also, to avoid fetching the entire module sources during dependency resolution, we store the module.bazel files separately in the registry, and the module.bazel file inside the source archive is ignored. In the Bazel Central Registry, we additionally require a presubmit.yaml file for each module version. You can specify a list of build and test targets for your supported platforms. Those could be the targets you want to expose to the downstream users, and a few tests that are well maintained and have a history of providing good signal and high quality test results. On Bazel CI, we have set up a BCR pre-submit pipeline to run those targets, and each pull request for adding a new Bazel module has to pass the pre-submit test before merging. With the information in the Bazel Central Registry, we also plan to implement more testing infrastructure to help module owners and especially rule set owners to maintain their compatibility with downstream projects as well as different Bazel versions. In the downstream test pipeline, a module can verify if a new version will break its downstream modules in the BCR. This could help the module author to declare the compatibility level more accurately. And in the Bazel compatibility test pipeline, you can test against a specific Bazel version and find out what version range of your module is compatible. This information can be stored in the metadata.json file of the module. We can later use it to help users resolve compatibility issues with Bazel. Currently, those additional pipelines are still in development, so stay tuned for more updates. Also, the Bazel Central Registry is still in the testing and ramp-up phase. We would like to encourage the community to try it out and modularizing your project as well as your dependencies and help maintain them in the BCR. You can check the BCR Git repository for more information. We're looking forward to hearing your feedback. So next, Xudong will talk about module extensions.
Module extensions allow you to write and use extensions in module.bazel files. They're functionally similar to today's workspace macros in that you can invoke repo rules to create repos, but differ in the sense that they get access to the entire dependency graph and can perform arbitrary non-hermetic logic, such as talking to your non-Bazel registries. In this example, the gray blocks are Bazel modules. You can think of each one as a module.bazel file. The tags are pieces of data that the user can specify for an extension to read. An extension such as Maven is evaluated once after all Bazel depths are resolved and gets to read all the green tags in the dependency graph. Similarly for cargo and the blue tags. Notably, the extension is not invoked once for each tag. Here we can see an example usage of a module extension called Maven in a module's module.bazel file. Note that this is not actually shipped in rules.jvm external yet. It's just an example. Extensions are defined in Bazel modules, such as rules.jvm external here, so add dependencies on them with Bazel dep as you normally would. Then, instead of using a load statement, use the special built-in function useExtension to bring in an extension into scope. You can use the dot syntax shown here to specify tags, which, as a reminder, are inputs to module extensions. Dep and pom here are tag classes defined by the extension Maven. The attributes here need to follow the schema defined by the tag classes. Note that you can even use labels pointing to files in the attributes, as with the maven.pom tag here. Any changes to the file will cause the extension to rerun. If the extension generates repos and you would like to use them in your module, you need to declare them with useRepo. This is in part to satisfy the requirement of strict deps. The repos that an extension generates are part of its API, so by reading the docs of rules.jvm external, you should know that with the tags you gave it, it'll generate a repo called org.junit and one called com.google.guava. You can then rename the repos when you bring them into scope, such as here to JUnit and Guava respectively. Here's the full picture for extension usage again. And now let's look at an example of the definition of a module extension. The picture is a bit more complicated here, but bear with me as I break it down. Extensions are defined pretty much how you would expect rules or repo rules to be defined. The slight difference is that a rule can have a few attributes, but an extension can have a few tag classes, each of which has a few attributes. And of course, there's the implementation function too. The implementation function gets a CTX object through which you can access the entire dependency graph and get your tags. Here, we collect all the maven.dep tags and flatten their cohort attributes to a single list. It's not shown here, but you can also get the pom tags here by calling mod.tags.pom. You can use the ctx.execute method to perform arbitrary logic, such as talking to the Maven central repository. Here, we call the Corsair CLI tool to resolve those Maven dependencies. After you gather information, you can create any number of repos by calling repo rules, just like in workspace macros. It's not shown here, but you can also register toolchains and execution platforms. Et voila! Note that module extensions are defined in exactly the same environment as repo rules, and today's repo rules don't need to be changed at all in order to be used from a module extension. So to recap, module extensions allow you to bring in external dependencies from non-Bazel registries and perform arbitrary non-hermetic operations such as configuring local toolchains and execution platforms and registering them. You might be wondering, what is the point of all this new complexity when repo rules can already do all of those things? The answer is that repo rules don't work well in a world where transitive dependencies can declare their own repos. In the example shown here, if both A and B declare a repo named foo, there's no good way to decide what should happen. In contrast, module extensions get a holistic view of the entire dependency graph and can thus make a more informed decision. And now I'll be talking a bit about the progress we made in the past year and our plans for the future. Those of you who read the original design doc may remember a very different picture, when Bzlmod was supposed to be a separate CLI tool, which when run, wrote out a workspace file for Bazel to consume. We actually spent a few months implementing this separate tool before realizing that there were insurmountable hurdles to feasibility and usability. In short, you had to run Bzlmod resolve every time your module.bazel file changed, or when any module extension.bzl file transitively included in your main repo changed. Having back and forth calls between Bzlmod and Bazel was also often awkward. So we pivoted to an implementation within Bazel itself earlier this year. One major win was the ease of use. You can just run Bazel build X and all your external dependencies will be automatically resolved. When we refer to Bzlmod now, we just mean the external dependency subsystem within Bazel. There's an experimental version of Bzlmod that you can use in Bazel 5.0 guarded behind a flag. this flag can actually already be turned on for Bazel itself. So you can build Bazel 5.0 with Bzlmod enabled using the modules that we put in the central registry. When you turn it on, both workspace and module.bazel files will work at the same time, with module.bazel taking precedence. Core functionalities such as Bazel module version resolution, overrides, and module extensions are all in place. Some stuff like log files, vendor mode, and dependency inspection is still missing, but we're working on it. Looking to the future, you can definitely expect more updates to ship in rolling releases. There might be breaking changes since we're still having extensive discussions about the implementation, which can have long-reaching and long-lasting effects. We'll be working closely with targeted migration clients, such as popular rule sets and prominent projects like TensorFlow. The next milestone would be to officially ship a stable version of Bzlmod that's turned on by default, with a flag to disable workspace handling. This will pose additional challenges, as finding an alternative for remaining workspace functionality and modularizing stuff bundled with Bazel will require careful design and migration efforts. We also want to be careful not to divide the ecosystem. And when Bzlmod reaches full feature parity and the migration effort is more or less complete, we can fully deprecate workspace and remove the code handling it. And that's a wrap. Thank you for joining us for this talk.